right. Just a reminder that the fourth problem set is due on Wednesday. It's been up since early yesterday, I guess. All right. So today I'm going to talk about household magnets, and to set the stage for that, it might seem irrelevant, but just to remind you what we did with electricity. So we did electricity, we're going to come over to magnetism, and later today we'll discover they're not unrelated. So with electricity, we discovered that there is electric charge in our universe. It's a conserved quantity. It shows up on some of the subatomic particles. Obviously, people didn't realize that at first. They just noticed that it existed, that certain things would acquire one type of charge or the other type of charge. That actually became sort of, those coalesced into positive and negative amounts of a single conserved quantity known as charge. And so we now sort of realize that around us is this conserved quantity charge, and we have objects that are positively charged and objects that are negatively charged. The main reason so far why we would even notice that it's there, that there is charge, is because materials fight unequally over some aspect of that charge. So we get accumulations of positive charge on one object and negative charges on another object fairly often. If you touch two dissimilar materials together, it's very likely that when you pull them apart, one of them will have acquired a negative charge and one of them will have gotten a positive charge. Of course, the total charge remains whatever it was before you started, because charge is conserved. But charge wasn't unknown to people hundreds of years ago, and it was certainly, lightning was known for forever, that is the same thing as this electric charge sort of sitting around is one of these things that we attribute, I guess, to Benjamin Franklin. But anyway, so we've got charge around, and charge, because it is attracted to opposite charge and repelled by like charge, it can have energy stored in it, in the forces between it and other charges, and we can call that electrostatic potential energy, because again it's a stored form of energy stored in the forces. And the amount of stored energy per unit of charge at a given location is the voltage of that location. So if there's a location where charge, always being positive charge, every unit of positive charge at that location has lots of stored energy. That's high positive voltage. And if there's a location where any unit of charge at that location has very low energy, in fact less than zero, meaning you actually have to do work on that charge to drag it away to far, far away, then that's negative voltage. And so we see there's voltage around. Wherever voltage is changing quickly with location, that is, there's strong voltage gradients, charge in that vicinity has strong forces acting on it. And we associate those forces that act on charge with the presence of this seemingly ephemeral thing, a structure in space we call an electric field. So electric fields push on charge, and we, at least at this point, the only cause of an electric field is the presence of other charge. So if I put a charge right here and it feels a force to your right, there's an electric field there. And the electric field there is evidently pointing to the right, and it's got a certain strength, which is associated with how strong that force is. And so far, we kind of assume that, well, if there's an electric field there, well, it's because there's other charge around. And the other charge is creating that field. Whether that field is real or just a fiction that we are using isn't clear yet. It is real, and I've told you that, but there's no real reason why you'd believe it. And so we got electric fields around, charge pushed around, and then we looked at charge moving around, carrying energy with it in that stored form, electrostatic potential energy, and dropping off that energy at say, at a light bulb to light the light bulb, going back to a battery to pick up energy, and so on. as electric circuits. So that's the background for going into household magnets. Just seems like we're completely changing story, but okay. So what's the story of household magnets? Well, just as people knew that there was electric charge around by virtue of things clinging to each other or pushing apart, people knew that there was magnetism around. Again, not a good historian of science, and I try to learn this stuff and I promptly forget it. But people knew that there was magnetism around. Mostly they would find it, a naturally occurring magnetism. Materials that certain types of igneous stuff that came out of lava and congealed had magnetic character to it, and it was useful for compasses. So people, I forget how long ago people realized that compasses were kind of a good thing. Somehow the Earth seems to have some magnetic influence, and these rocks that cooled properly and had the right chemical characteristics had magnetic character, and they would tend to line up the magnetic rocks would tend to line up with the Earth's magnetism, and so you could have compasses, and it was all very nice and useful. But strong magnets, the type that we're now used to having around the house, basically, or as even practically as toys, they're relatively modern discovery. And okay, so magnets were known, but so what are the characteristics of magnets? Well, they're naturally occurring things, so I'm going to just pretend that we sort of naturally occurred pretty decent magnets, just sort of showed up. And here is one, for example. And what we discover with magnets, we sort of play around with them, that is that if I have a magnet here, and this one's, I think in every case we've got here, the magnets have two ends. There are a lot of bar magnets up here. So this is just a prop. This is not a magnet, but somebody made it for the department, so it's kind of cool. Anyway, the ones I've got up here are all arranged such that they've got two ends, because they're bars, right? And the ends are labeled by both red and the letter N, which is for north, of course. And the other end is white and labeled S for south. So, but what's the story here? Well, I've got one of those in my hand. I've got another one on a swivelly mount so that it can turn. And the observations are these. If I bring the white end, the south end of this magnet, up to the north end of that magnet, ooh, they like each other. There's some sort of attraction between those two. On the other hand, if I take the same end, the south end, and go over to the other end of this magnet, the south end, they hate each other. So right off the bat, we start to see that there are both attractive magnetic forces and repulsive magnetic forces, which is not too big a surprise. We saw the same kind of thing with electric charge, although, of course, this has nothing to do with electric charge. Okay. And the other thing is, if I use the red, the north end of this magnet, of course, it attracts the south pole and repels the north pole. So it's just, in a nutshell, we seem to have two types of magnetic something, and when we bring like types of it together, they repel, and opposite types of it together, they attract. Well, this does sort of kind of sounds a little bit like electricity, except this isn't electric charge. This is something different. This is magnetic stuff. And so there seems to be another conserved quantity around, and I haven't yet proven or demonstrated that it's conserved, but it is another conserved quantity. And we can't call it charge because charge is taken. And we can't go positive and negative because they're taken too. So what we'll call it is something different. We'll call it pole, P-O-L-E. And we can't have positive amounts of pole and negative amounts of pole, although that would be perfectly reasonable. It's just going to get confusing. So I'll call it North Pole and South Pole. And North Pole really is a positive amount of a conserved quantity called pole, and South Pole is a negative amount of that same conserved quantity. And otherwise, the rules are very similar to what we observe with with electric charge, the forces between two poles are attractive if the poles have opposite signs, that is north and south, not two of one. And it's repulsive if they are the same. And the forces get stronger as you get closer. What is the rate at which they get stronger? Well, it turns out the forces between poles, as with the forces between charges, are proportional to 1 over the distance, the separation squared. So as the separation gets smaller, 1 over a small number gets big. So the forces get big. So the forces, it's another inverse square law, a term I've used occasionally here. Nature loves inverse square laws, which means that the forces get stronger as 1 over the separation squared. Gravity's like that, electricity, the forces between electric charges like that, and magnetism is like that. The forces between magnetic poles are like that. So that's the starting point for the story here is that there's a new conserved quantity. It's got amounts that are positive, we call them north. Amounts that are negative, we call them south. Opposites attract, likes repel. Forces get stronger as you get closer. Wow, it's just like electricity, except, there's a big difference, important difference. The important difference is it's tough to find just an object that has just north pole on it. These magnets have a north end, but oddly, they always have a south end. So here's another one like this. Here's another magnet. It's got a north end, south end, but I can break it. So there's the north end, is doing what it's supposed to. The south end is doing what it's supposed to. And I can break this magnet. It's actually pre-broken, snap. And so now I've got an object that's all north, right? Another one is almost all south. So the question is, what are the new ends, the broken ends like? And just because I haven't done it for a while, I ask it for you as a question. Say what you think. There's no real reason you would anticipate the answer, but so if I break, it's North Pole at one end, South Pole at the other, if I break it in half, the new ends will be, and what will they do to each other? Oh, I got to start the story. Any questions about the question? I don't know why I have to press that thing, but I do. We'll go to 20 seconds after, and then I'll show you, we'll look and see what the answer is. 5, 4, 3, 2, 1, 0. Okay, so the majority are going for a track, but there's substantial the other possibilities. So let's try it. So I'll come back here live. And so this is basically the story. We've broken the magnet. This one's all red. This one has a red tip. They should repel if they're both, if this really is a north red north. This guy's all north. They should repel. No, they stick. They love each other. So what is this? And what is that? Well, let's try it. This is south. Well, I can prove it's south. The obvious way to prove it is see what it does to the North Pole. Definitely south. What's this guy? Is this guy, maybe this guy's south too? Nope. It's north. It's a real North Pole. So when we broke it, we end up with a North Pole here that's colored red, and that's appropriate. All good. This guy, we have nothing to guide us yet because it's all red. It sure seems like it should be all North Pole. So let's try the original North Pole. This is the original one. Yep, it's north. Really is. How about the other guy? It's bright. It's red. It hates south. It likes north. It's a south. So this guy, when we broke the magnet, the original North Pole is still there. But the bottom part of that chunk that that was labeled North Pole, it's actually now a South Pole. And so we've got a South Pole on the bottom of this guy, North Pole on the top of that guy. They like each other. That's why they attract. And where this is heading, so the answer is A, the ends attract. And where this is heading is, the net pole on this guy, when I first brought it up here, the net pole, where you're adding the North Pole, which is positive amount, and the South Pole, which is a negative amount, when you add them together, it's exactly 0 to all decimal places. Well, that's odd. And if you break it in half, and you have 2 objects, the net pole on this guy, it's 0 again to all decimal places. And the net pole on this guy, it's 0 to all places. The weird thing is, objects in our universe, to the best of our current ability to determine it, always have net pole 0. No one has ever found and proven the existence of an object that has a net pole other than 0. If they did, that would be called a magnetic monopole. And people have been looking for magnetic monopoles, that is a pure North Pole or a pure South Pole. They've been looking for them for at least 40 years. The most convincing observation of one that was never confirmed, it was never reproduced. It was seen one time with insufficient clarity to be sure that they saw anything. It was while I was a graduate student. It occurred in the lab below me on Valentine's Day, many years ago. And the joke was that they registered the presence of a single, I don't know if it was North Pole or South Pole, going through their apparatus. And they never saw it again, and no one has ever seen one since. And so the joke is that maybe that was the only magnetic monopole in our part of the galaxy or the universe. And they saw it, and they'll never see it again. Had it been seen, it would have been and proven to exist. Of course, it would have been one of these Nobel Prize winning events. And the students involved were, of course, very excited. And alas, it didn't really turn out well. Furthermore, the guy who found it was from UVA, but not here. I mean, this is another school. Anyway, so he had gone to undergraduate here, and his father was a professor here. Anyhow, we've never seen magnetic monopoles. It's not sure they don't exist, and there may even be theories that require them to exist, but no one's ever seen one. So the weird thing is that we never see isolated pole, and yet we see lots of magnetic stuff around. And so where the heck does magnetic stuff show up from? As with charge, magnetism shows up with subatomic particles. It's just there. It's part of their life, part of their existence. Things like electrons, protons, they are magnetic. It just comes with them. However, they all have net pole 0. So that's weird. What does that mean? It means they're all effectively like bar magnets. They have a north end and a south end. They don't just show up as a north end. That's quite different from electric charge. An electron truly has a net negative charge, no problem. It does that just fine. Same with the proton has a net positive charge. An electron does not have a net north pole. It has both a north pole and a south pole. They're equally strong and therefore sum to 0. All right? That's the way it is. The most significantly magnetic particles for our purposes, for life around your house, or right here, are electrons. For what they are, they're quite magnetic. How would you ever see that they're magnetic? You don't have one electron to play with. When electrons get together and assemble into atoms, and from atoms then get together and assemble into materials and stuff like that. Most of the magnetism that is present intrinsically in electrons is canceled, alas. Why? This goes back to stuff that you have encountered in the chemistry course when you've talked about what would you have talked about? The bonding between chemicals. A lot of times, electrons are magnetic. I got to tell you a few more details about them. Electrons, not only are they magnetic, but they carry with them another interesting conserved quantity, one that we've already encountered. So they got lots of conserved quantities. They got magnetism, which is conserved. They got electricity, electric charge, which is conserved. They also have angular momentum, which is conserved. And this you've heard about in chemistry. You've talked about spin, probably the spin of electrons. They show up in stories about chemistry and how atoms are built and how things stick to each other. Electrons have an intrinsic quantity known as spin, which is a small unit, a small portion of angular momentum, and that's associated in part with quantum mechanics, which makes it complicated. But to make it as simple as possible without making it wrong, electrons can be thought of as having angular momentum. If you want to think about around a vertical axis, we've seen that things rotating about a vertical axis carry angular momentum. This is angular momentum up, right? According to the right-hand rule. This is angular momentum down. And electrons carry as little angular momentum as sort of anything can possibly carry. Just a tiny smidgen of it. And it shows up, if you look for its vertical portion of angular momentum, you get one of two values. You either get a tiny morsel of upward angular momentum, like this, or a tiny morsel of downward angular momentum, like that. So we just talk about them as spin up or spin down. You've probably done that. It's a little, it's oversimplified in ways that are important to physicists primarily. But with that angular momentum comes the magnetic character. And I should know whether a spin-up electron has a north pole at the top or the bottom. I don't know it offhand. I can't, while standing here, can't verify any particular gas. But so the point is that all the spin-up electrons are like bar magnets that have a particular end up. And all the spin-down electrons are like bar magnets that have the other end up. So if you collect a whole bunch of electrons, if you get them all so that their angular momentum is pointing upward, so they're all, in effect, they're all spinning like this, in effect. Then they're going to all have one pole up in common, the other pole down in common. They'll work together to have a big magnetic influence. They'll basically start to behave like a big bar magnet. They'll all work together. And if you take that cohort of electrons all spinning in the same direction and bring them up to one of our swiveling little bar magnets, like a compass, you'll get its attention. It'll orient. It'll bring its opposite pole as close as possible. All right, so that's a real effect. You really would do that. But it's hard to get a whole slew of electrons all being spin up. How would you ever do that? And it turns out that actually chemistry is causing you trouble typically. When you assemble an atom, you take a bunch of electrons, all by themselves, they're kind of going to get lonely, but furthermore, they're going to repel each other. They're going to hate this arrangement. So they're all going to go flying off to the four winds. So if you actually want to bring a whole bunch of electrons close together, you really want to assemble them into something like atoms, and from the atoms into materials. Well, when you do that, problem shows up. When you start to bring electrons together to form an atom, the electrons like to go into the arrangements that have the lowest total potential energy. They like to fall down, settle down to the lowest energies they can, in much the same way that balls like to roll downhill and carts like to go down ramps, all these things trying to get rid of extra energy. So most of the atoms that you encounter are in what are called the ground state. You've also talked about this somewhere in chemistry or other. The electrons go in there, and the story is, and we'll see later this semester, the story is they're not little planets going around the nucleus. In the original picture of an atom and an atom's electrons, they're more complicated than that. They have a lot of wave-like character to them. But the point is that they snug in as close as they can to the positively charged nucleus of the atom in order to minimize their total energy. And when they do that, for quantum mechanical reasons, they are limited in how they can arrange themselves. They can't be any old which way because they are not little planets. They are little waves. And there are only certain waves that can actually be there. And quantum mechanics has a rule that is observed in nature called the Pauli exclusion principle, which is something you've also probably heard about. And what it says is that two electrons that are indistinguishable, or two particles that are indistinguishable, but in this case electrons, that are indistinguishable cannot be in the same quantum mechanical state, the same quantum mechanical wave. And what that means for us, assembling an atom out of suppose we're assembling some big atom, I'll pick one at random, iron. And iron has, I should be able to count the electrons. It's something like 16. Anyway, do I think monopoles exist? Undecided. It's too far. It's far enough away from me in a field that I don't have a valid guess. Anyhow, so with iron, iron's been something that I've dealt with a lot in my life, and yet I can't tell you be super confident it's got 16 electrons. But when you assemble iron, you're putting all the electrons in. The electrons, because they want to go into the lowest energy orbitals, another word you've probably heard before. These are the waves that they're allowed to go into. They want to get in as close as possible at nucleus and minimize their total energy. They would love to all be together in the lowest wave if they could, but the Pauli exclusion principle forbids that. Only one identical, one indistinguishable one can be in there. But there is a way you can distinguish two electrons from each other and stick them in that lowest possible orbital. Give them different spins. That is a distinguishing factor. A spin of electron is distinguishable from a spin down electron. They are not the same particle then, and you can put one of each in that lowest energy wave. So in assembling atoms, iron in particular in this case, but all the atoms, the electrons, as they try to snug in as close as possible to that positively charged attractive nucleus, they tend to pair up. You tend to put in, whenever possible, one spin up electron and one spin down electron into the lowest available arrangement, wave arrangement. And that's great for energy, but it's terrible for magnetism, because if you put a spin up electron and a spin down electron in the same situation, they're north pole up, north pole down, north pole down, north pole up. They cancel, south pole up. Their magnetism cancels. So the magnetism goes away. So when you take electrons and assemble them into atoms, electrons themselves are intrinsically very magnetic. When you assemble them into atoms, an awful lot of that magnetism, this is the bottom line, gets canceled. It gets canceled for reasons having to do with energy. Trying to get the electrons as low energy as possible means you got to pair them up. I don't know, there's probably some analogy like people getting on a train. You keep having to put two together on every car. And so if that were the only story around, magnetism would be pretty much absent in our world. The only situations in which you would get you would notice that electrons are magnetic in materials is if you had atoms, is for atoms that have an odd number of electrons. Because you run out of pairs, right? The last electron is by itself. Its magnetism is still noticeable. So it turns out atoms that have an odd number of electrons have a small amount of magnetism remaining, because they can't The last electron's by itself, it's magnetic, hey, you notice it. But an awful lot of the atoms that have even numbers of electrons have lost, well, a good number that have lost all their magnetism. Helium, for example, is magnetically dead, nothing. It's got 2 electrons, they're paired up, put out of our misery, no noticeable magnetism there. They don't pair up perfectly. Electrons don't pair up perfectly, and why not? Because there is another quantum mechanical, there's a quantum mechanical effect around that the atoms and electrons in the atoms make use of. Again, the electrons are trying to minimize their energy, and putting 2 of them in the same arrangement means that they both get to use that low energy arrangement. That's really good. However, they're both in that arrangement and they don't like each other. They repel. So putting 2 of them in the same quantum mechanical orbital is valuable. I hope that, I'm being cavalier about talking about orbitals. Orbitals are the waves that electrons can live in atoms. We'll see more about that later in the semester, but they are the quantum mechanical version of the little planetary orbits that you can imagine for the real planets going around the sun. It's perfectly reasonable to think of them as essentially billiard balls going around a central big billiard ball, and they have very well-defined locations and all that. Life is simple. When you go down to the tiny scales associated with atoms, that picture runs into trouble because of quantum mechanics. And quantum mechanics is subtle and complicated, and it's not very easily observed, which is why it took until a little over 100 years ago for people to discover, there's something wrong with how we picture things. And so one of the ways in which quantum mechanics popped up was that atoms, which are composed of these positively charged nuggets at the center, the nuclei, and the electrons going around them, if they were just little planetary systems, they would have various misbehaviors that we don't observe. So what are they doing? Well, it's really electron waves sitting around the nucleus, not little billiard balls going around the nucleus. And those waves have interesting structures, just like the waves on a plucked violin string or the head of a drum vibrating. All those fluctuations, or the water in a basin sloshing back and forth. There's a lot in common. And you can get the water sloshing in a basin. It's got certain structure, that's natural structures to it. You get the string vibrating on a guitar. It's got certain natural structures to it. It's got pitches that are controlled by characteristics of the string. You can't make a guitar string vibrate at the wrong pitch. It's got a pitch. It's determined by its base. And the same is true of electrons. The waves that are electrons in atoms, they've got certain, in a sense, pitches. And so you try to put them in the lowest energy pitches. So coming back then to there's a competition between putting 2 electrons, one spin up, one spin down, together in a lowest energy configuration, lowest energy orbital. That is great as far as using the lowest energy orbital as efficiently as possible. We've got 2 in it, that's great. We don't have to use the higher energy ones. However, putting 2 electrons in the same arrangement means they're effectively very close to each other. They're sharing the same traveling environment, and they hate that. They repel. So it turns out quantum mechanics has a way of keeping them out of each other's hair that has to do with giving them the same spin. If you give them the same spin, they cannot be in the same wave at the same time. There are ways in which that is useful. It gets them apart, and it reduces their electrostatic energy by making them the same spin. It's called the exchange interaction, and it's not worth pursuing much beyond that. But quantum mechanics says that no, don't always pair them up so they're oppositely spinning oppositely and therefore magnetically dead. That's good for getting the lowest energy orbital, but we can do better sometimes by giving them the same spin so they stay apart, so they can't share the same wave. And that happens in atoms. So some atoms have actually quite a lot of magnetism left, iron being one of them, manganese being even more. Some of the atoms have quite a surprising amount of magnetism left from the electrons because of this exchange effect where the electrons are trying to stay away from each other. And they're using quantum mechanics to do it. Okay, so magnetism, not all is not lost, even in atoms with even numbers of electrons. And I'll try to stop the story here pretty soon. When you bring those atoms together and make materials out of them, the tendency for spin pairs to form again shows up. So it tends to, when you bring two atoms together, for example, I don't know, 2 carbon atoms, to pick them at random again too. 2 carbon atoms, you bring them together and they link to each other by way of what you've, I hope, have heard is called covalent bonds. They begin to share electrons. And when they share electrons, they love to share those electrons as a spin pair, one spin up, one spin down. And what that means then is that the atoms, carbon atoms, can have magnetism. And do they? Yeah, probably do. But when you bring them together and bond them to each other, the magnetism gets canceled again. And when that happens, you lose that electronic magnetism again. Where this goes is that most organic molecules, molecules of life, the ones we're made out of, which are held together by covalent bonds, as a separate observation, the sharing of electrons, they tend to share the electrons as spin pairs. In the jargon, spin pair means a spin-up electron and a spin-down electron, a magnetically dead system. And therefore, most of the molecules of life are magnetically dead. The electronic magnetism is canceled essentially perfectly, and you wouldn't notice they're magnetic at all. So that's not completely the case. There are subtle effects around with magnetism. These are often used, they're used in modern life, for example, for magnetic resonance imaging, MRI. You know, what are they doing? They're using magnetism to see where your molecules, atoms are in you. And they're looking for magnetism, and they're looking for the effects of any magnetism in the vicinity of the particles they're looking for. Anyway, the presence of some subtle magnetism in people and organic molecules is useful, and it's part of modern medicine. But most organic materials are non-magnetic. So blocks of wood, I mean, yeah, this is cute. This is fun, but it's not real. Wood doesn't care about magnetism. We don't care about magnetism. You will have opportunities your whole life to be buying magnets to improve your circulation or make you feel better, whatever. You know, all likelihood those have no effect because you basically don't. Your body is nearly completely unresponsive to magnetism. So why is there any magnetism around at all? It's because there are some materials in which that exchange interaction effect, the tricks for keeping, the quantum mechanical tricks that materials or systems would use to try to keep the electrons apart and therefore reduce the energy, reduce the repulsion problem, they do survive into some materials. Not many. One of the most important materials that the magnetic effects survive into is iron. So your refrigerator magnets stick to the iron because iron is intrinsically magnetic. It has, the electrons in there are not all spin paired away to nothing. So iron is intrinsically magnetic. I need to show you how it's magnetic and how it's magnetic, how you notice that. Before I do a few cents about iron and steel, if you're like me, in your situation back then, I didn't know the difference between iron and steel. Iron is an element. In principle, iron is a pure chemical. You know, it's just iron atoms. It might have a few impurities because everything's got impurities. But iron is a pure material. It's a relatively soft, I mean, on the grand scheme of things, it's pretty hard, but it's soft compared to most of the things you encounter made out of iron for good reasons. It is magnetic, as we'll see. is not very useful. It's not, and therefore not very common. It has certain uses that are good, but you can make stronger stuff by adding other chemicals to the iron, and those are the steels. So steel is by and large, is iron to which chemicals have been added, the most important of which is carbon, have been added to give it more strength and to otherwise change some of its characteristics. And it turns out adding a fraction of a percent of carbon to iron, and you might think, carbon in iron? Like, what's that? It can go in there. And in certain circumstances, it actually dissolves in the iron. At high temperature, it dissolves in the iron. And when the temperature drops, it comes out of solution in interesting ways that strengthen the iron. And that's the world of steels. But most steels retain the same structure that pure iron has at the level of the atoms and the arrangements of the atoms, and therefore are still magnetic. That's not true of all steels. You can gum up the steel enough that it changes its crystal structure. The arrangement of the atoms. Believe it or not, metals are crystals. Virtually all metals are crystals. They have neat arrangements of atoms with some disorderly things, but basically they're arranged the same way that a beautiful arrangement of oranges at the grocery store will be set up, where they're all lined up in rows and stuff like that. The atoms in most metals are like that too. And the choice of the arrangements matters. Ordinary iron and most steels, well, a lot of steels, have a certain arrangement that is intrinsically magnetic. There's another common steel arrangement that is non-magnetic. That one shows up in most cheap stainless steel. So ordinary cheap stainless steel, the stuff that's kind of flexible, probably like the stainless steel that's used in cafeterias, where the forks are all kind of snaggle-toothed because they bend so easily, they're non-magnetic. It's, it's made mostly of iron, but it's lost magnetism. So most iron, however, is magnetic. And I can show you, how would I show you that it's magnetic? Well, I'll show you that most metals are non-magnetic. So this is a chunk of copper. And if I bring copper over to this guy, to this swivel guy, it doesn't give a hoot. Okay. Same with aluminum. Here's aluminum. Aluminum's non-magnetic. So if you have a refrigerator that's made out of aluminum, you can't stick refrigerator magnets to it. Copper, no refrigerator magnets. Certain types of stainless steel, no refrigerator magnets. Steel. Steel now, we get a response. This is not a magnet, but it is made of a material that has effectively little magnets in it. Steel, at the microscopic level, has little patches, which are called domains, that are highly magnetic. The electrons within one of those little patches, and these are really little, they're atomic scale sizes. There'll be a patch where all the electrons will be, the leftover, the magnetic electrons, the ones that are not canceled, will all be spinning the same direction. And you could go label that domain, it's called a domain. North Pole and South Pole, you can put the label on it. There'll be another domain nearby with its own arrangement, and you label it. And in naturally occurring steel, which this essentially is, those domains have no reason to all line up the same way. If they did, they would create, suppose they all lined up the same way and they put their North Pole on top and their South Pole on the bottom. If they do that, there will effectively be a big North Pole at the top of this stick, because they'll all sort of contribute to it. And they'll all contribute to a South Pole at the bottom. So it'll be like a large North Pole at the top and a large South Pole at the bottom. And those poles will attract each other. They will actually, they're kind of unhappy. It's like you've taken North Pole and South Pole that used to be together and you pulled them apart. And they're against their own attraction. They don't like this. They store energy when they're like that. So having a magnetized system actually has energy stored in it. And if this had a North Pole at the top and a South Pole at the bottom, it would have magnetic energy stored in it, magnetostatic potential energy. And it would love to get rid of that, and it typically does. It does that by taking the domains that are all pointing the same direction, they all have their North Pole up, and flipping some of them upside down. So one of the ones that was North Pole up becomes North Pole down. And that reduces the energy of the system. And magnets love to pair up, like if I put two magnets side by side, they love to pair up north, north, south, south. So that's what happens. The domains all flip up. They flip alternately, essentially, and kill each other's magnetism off. So to have, when you have ordinary iron or steel just sitting around, it's typically composed of lots of little magnetic domains, microscopic in size, pointing in somewhat random directions in such a way that their magnetism on average is pointing in nowhere. There's many North Pole up little domains as South Pole up domains. There's many North Pole left as South Pole left, all scrambled. So how would you get them to line up? Well, you get them to line up by bringing another magnet, a real magnet, one that's got a strong pole, nearby. When I bring the North Pole of that swivelly magnet near to my piece of iron, it polarizes the iron. It's the same idea as, remember I was polarizing like the wall with a charged balloon, electrically charged balloon? It causes a rearrangement. The balloon causes a rearrangement in the charges in the wall. In this case, the North Pole, that swivelly magnet, causes a rearrangement of the charges, the poles in the iron. It rearranges the domains. And to illustrate that effect, I'm taking longer than maybe I wanted to, but here we are. Here, we're going to look down on this. I've got a lattice here of little tiny magnets. And we're going to look down on it from above. There we go. And initially, they're pointing somewhat randomly. There'll be some amount of alignment because locally a few of these want to align with each other. They notice each other are there, but by and large they're pointing in random directions. See that, right? If I bring a strong magnet around, I will orient a lot of them. So now I've lined a whole bunch of them up down here near where well, you can't see the magnet. Now you can see the magnet. I've lined them up. So I have polarized the material. Now it's magnetic polarization instead of electric polarization. This North Pole here has brought the South Poles of a whole bunch of nearby magnets toward it. And this is now magnetized. Previously, it had no noticeable magnetism except at the tiniest of distances. When it was a big scrambled mass, there's no spot on this that's mostly North Pole, and another is mostly South Pole. It's all every which way. Oops, that was fun. But if I come in with a strong magnet, I line it up, and that's what you do when you bring your magnet up to a steel refrigerator, iron or steel refrigerator. Is the refrigerator wasn't magnetic, and it won't be when you take the magnet off. But while the magnet is there, and say its North Pole is very close to the surface, the iron and steel in the refrigerator will have turned its South Poles toward the North Pole. And now because they're closer to the North Pole on average, than the South Poles are, than the North Poles are, there's a net attraction. The refrigerator magnet is still attracted by opposite poles and repelled by like poles. But those like poles and opposite poles have shifted spatially so that the opposite poles, the attractive opposite poles, are closer. So the refrigerator magnet sticks. So just to tell you where we're going with this, the magnets that I have up here are mostly iron, but not pure iron. They are iron and therefore have these magnetic domains, but they're special irons that have the ability to be lined up by an external magnet and then remember that alignment. They're called magnetically hard materials. You align them and they stay that way. They remember. And that's the case of all commonly occurring permanent magnets. They have been lined up. and they were remembering it. But we need to look at, down the road, we need to look at how do you line up, how do you create the original magnet to line everything up with? And yeah, that'll be on Wednesday. We'll do that. So thanks.